In this video, we're going to go through average atomic mass. So let's begin by looking at this hypothetical student's grade. So for the formative category, they have a 98%. So really does a great job of turning in their homework. Summative, 4%. Not a good test taker, hasn't turned any of the labs in. Are they going to pass? Well, your answer should be no. They're definitely not going to pass. The reason they're not going to pass, as I'm sure you can look and imagine, the summative grade is worth 80%, and they have a 4% in that category. Formative, yeah, they got a 98%, but that's only worth 20% of their grade. So because they did so poorly in the summative category, they're definitely not going to pass. We'll come back to this concept of weights in just a second. So let's take a look at this atom. What element is it? Well, it's got one proton, one electron. Anything with one proton is hydrogen. So this is hydrogen. What about this element? One proton, one neutron, one electron. It still only has one proton, so this is also hydrogen. All right, well, what about this element? One proton, two neutrons, one electron. It still only has one proton, so this is still hydrogen. These are called isotopes. They're all hydrogen, but they have a different number of neutrons, so that makes them isotopes. Okay, well, these isotopes of hydrogen actually have special names. So hydrogen without a neutron is called hydrogen. Hydrogen with one neutron is called deuterium, and hydrogen with two neutrons is called tritium. So the mass of hydrogen is 1, the mass of deuterium is about 2, and the mass of tritium is about 3 atomic mass units. So then, why on the periodic table is a mass of 1.0078 listed? Because I'm confused here. So so hydrogen is 1, deuterium is 2, tritium is 3. So if we average those numbers, 1 plus 2 plus 3 is 6 divided by 3. 6 divided by 3. If we did a simple average, that would give us an answer of 2. And 1.0078 isn't anywhere close to that number. So where did this number come from? Let's take a look at this particle diagram. All right, so like the blue would be regular hydrogen, the black dots would be tritium. Sorry, the black dots would be deuterium, the second one, and then tritium would be the yellow one. Well, if you notice, there's a lot more of the blue dots than the black dots, and there are more black dots than yellow dots. So there are more blue dots, which is closer to the number 1, and deuterium is, remember, close to 2, and then tritium is 3. So our average seems to be more reflective of the isotope that only has a mass of 1. Again, there aren't very many deuterium, and there was only one tritium. So our mass is closer to the isotope that we have the most of. So we can actually measure how much of an isotope is in a sample. We have this fancy machine called a mass spectrometer. Really cool machine. And it will put out a graph that looks like this. And it essentially just measures or counts the number of atoms of a particular isotope. So it separates them by mass. Okay, and it gives you this readout right here. So if we were to get a readout for hydrogen, deuterium, and tritium, it would look something like this. And if you notice, hydrogen is pretty much 99.999% of all of the hydrogen that occurs in nature. There is some deuterium out there, 0.001% of all the hydrogen is deuterium. And then trace means there's a very, 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 very small amount of tritium that exists in nature. So again, this number, this atomic mass that you see on the periodic table represents most often the most abundant isotope. Now, it's not always the most abundant isotope. If you have some that are very close together and the masses aren't as concentrated as they were when one isotope, then it might be a little different. But in many cases, the most abundant isotope reflects the atomic mass. To calculate average atomic mass, we use this formula. Okay, now we got the fancy E symbol in here, which may scare a couple of you that aren't very, really into math. So this just means the sum of. So what we're going to do for every isotope, we're going to multiply its mass times its abundance, and we're going to add all those values up. And then when we're all done, we're going to divide by 100. So let me show you how this works. So it says a hypothetical element is found to have the following isotopes. Element 40 has, there are 96.94% abundance, and then 39.96 is the atomic mass for element 40. 44 is 3.06% abundant, and then 43.96 is the atomic mass units, the mass of that isotope. So it says, using the given information, calculate its atomic mass. So we're going to take for each element, we're going to take its mass, and we are going to multiply it by its abundance. So I did that for element 40. Let's do the same thing for 44. Okay. So let's do the first one. So we've got, let's see, 39.96 times 96.94, and we get a really big number. So 3873.7224. And then for our second one, we got 43.96 times 3.06. We get 134.5176. So let's add those numbers up. So 3873.7224. So there's our number right there. So 48.24. We take that number and we divide it by 100. And we get 40.0824 as our answer. Now, does that answer make sense? So our smallest number was 39.96, and our largest isotope was 43.96. Our average has to be between those two numbers. Okay, so our answer has to be between those numbers, which it is. 40.08 falls between 39.96 and 43.96, so that answer is okay. If I got a number that was 15, for example, that's way less than my smallest number. That doesn't make any sense. All right, let's do another one. This one says, what is the atomic mass of neon, giving the following information regarding its naturally occurring isotopes? Same thing. We're going to take each mass, multiply it by its abundance, add them all up, divide by 100. So 19.992 times 90.48. Then we have 20.994 times 0.27, and then 21.991 times 9.25. So let's get to work here. Let's see, we've got 19.992 times 90.48, and we get 1808.87616. Okay, and then our second one, we have 20.994 times 0.27, 5.66838. All right, and then our final one here, we have 21.991 times 9.25, 203.41675. Okay, so let's add all those up. Okay, so we add them all up, and we get 2017.96129, and we're going to divide that by 100. The reason we're dividing it by 100 is because we have percents here, and we're basically getting it from a percent into a number. Okay, we get an answer of 20.1, let's just call it 20.18. Okay, now does that answer make sense? Again, we want to look between our smallest number and our largest number. Does our answer fall between those? And yes, it does. So this would be a good answer.